Hello, everyone. Good morning, good afternoon, wherever you are in the world. And yeah, we are starting one more round of the ASTRAIOS webinar series. And today we will count with the presentation of Professor Claudio Persello. And just a brief introduction about ASTRAIOS. ASTRAIOS is an EU-funded project that is working on identifying the existing space-related education and training across Europe and the future demand for space skills in the European space industry. Also to identify actions to align and improve the career pathways into the sector. So the project started in January 2023 and spans over 3 years. And we are now in the final year of the project. And this webinar is part of the ASTRAIOS webinar series and helps us to reach the goal of improving the existing training materials and developing new ones to fill the gaps between the supply and the demand for the space education and training courses. So in today's webinar, we will have a presentation about the machine learning and the Earth observation for tackling the sustainable development goals. And we will count with the presentation of Professor Claudio Persello, who is an adjunct professor in the Faculty of Geoinformation Science and Earth Observation of the University of Twente. He is our colleague here in the Department of Earth Observation Science, and his main research interests are in the context of machine learning and deep learning for information extraction from remotely sensed images and geospatial data. Activity includes investigating and developing dedicated deep learning techniques for various remote sensing data and multiple applications, focusing on societal and environmental challenges. And he's particularly interested in combining deep learning and Earth observation to address and monitor progress towards the Sustainable Development Goals. I will give the floor for Professor Persello, who is on my side actually here in the room, and ask him to complete the introduction of himself if he wants, and have your time for your presentation. Thank you very much, Claudio, for joining us in this series of webinar.
Thank you very much, Ryan, and thanks all of you for joining this webinar today. So I'm Claudio Persello, as Ryan mentioned, working as a colleague here at the University of Twente, Faculty ITC. Today I will talk about machine learning, in particular deep learning for Earth observation applications in support of the Sustainable Development Goals. And today I will focus specifically on SDG 2 and SDG 11, so more on food security and urban application, urban sustainability. So let me just directly jump into the motivation of the research that we are carrying out. Why do we need machine learning for Earth observation? So probably most of you, if you are working in the domain, are aware that currently we have large volumes of Earth observation data acquired by different platforms, by satellites, aerial platforms, also drones or UAV. And this different sensor acquire very detailed information in terms of spatial resolution, in some cases also in terms of spectral resolution. Not only the quality is increasing, the quality as well, with several constellations also of nano satellites that acquire data with very short revisit time. And one thing also I want to mention is that we currently have the opportunity to have large, open and freely available Earth observation data like those acquired by the Copernicus program. They allow us, so they provide us huge amount of data, so tens of terabytes of data are acquired every day. So this is a very good opportunity for us to monitor and to map, to develop several applications based on this data. However, the main challenge is how do we actually extract useful, actionable information from this huge amount of data. So here is where machine learning, AI comes into play. And basically, these advanced data analysis techniques allow us to translate the raw data, the data is acquired by the sensor, into useful products like maps, like different kinds of maps and geospatial products. Most of the time, the type of product we look at are 2D maps of different kind of land covers or even crop type. Sometimes are specific type of maps like cadastral maps or field boundary maps. You can also think of extracting information in 3D, and if you also want to involve real-time information, you can think of using Earth observation in support of geospatial digital twins, which is currently also a very hot topic. What I want to emphasize is that the combination of machine learning and Earth observation allow us to tackle several geospatial applications. And many of them allow us to address problems at the local level, to monitor, to map natural and urban environments, and provide information for decision makers. But today, what I want to emphasize is beyond that, Earth observation now allow us also to address global challenges, phenomena that needs to be studied, needs to be understood by considering how the entire Earth systems behave. So in that sense, the global coverage of this data allow us to monitor and to study phenomena like urban growth and poverty that are spreading all over the world, and address challenges related to food security and climate change, just to name a few. So that's the kind of angle that we want to look at things today. So we want to see how actually Earth observation and machine learning allow us to address these challenges. And some of these challenges are actually considered in the Sustainable Development Goals. So these goals developed by the United Nations are like a plan of action to address, to end poverty and to reach peace and prosperity by 2030. So the Sustainable Development Goals are very ambitious goals to be reached now in less than 5 years, but are also like a motivation for us to work on addressing these very important problems. An important aspect of this agenda is that it's like for the first time a truly data-driven framework, and is based on the idea that if we want to achieve these goals, we need to be able to track progress about several indicators that measure how well we are doing in respect to all these different goals. So the agenda includes 17 different goals and 169 targets and 232 indicators. Some of these indicators are very specific and measurable quantities. And in fact, they are very important to indeed track progress and see how we are doing in respect to achieving these target goals. Good news for us, for people working in Earth observation, is that approximately 34 of these indicators can be directly or indirectly informed through Earth observation data. So in that sense, with our expertise, we can actively contribute in monitoring progress and achieve several of these sustainable development goals. So in the rest of this presentation, I will focus mostly on two specific SDGs. So SDG 2 on zero hunger and SDG 11 on sustainable cities and communities. So let me start with the first topic for today. So it's about, let's say, related to SDG 2 or in support of SDG 2, which aims at ending hunger, achieve food security, and improve nutrition and promote sustainable agriculture. So that's the general goal. But if we look at specifically target 2.3, it aims at doubling the agricultural productivity and incomes of small-scale food producers. So that's the topic I would like to cover today. So it's about mapping and basically acquiring information about agricultural resources in smallholder farms. So smallholder farmers are all over the world, but they are the majority, the large majority of the cropland that is cultivated in Africa. So is an important challenge. And why is it a challenge? Because smallholder farm communities are typically very vulnerable because their cultivations depend on rains. So it's fundamentally dependent on weather conditions and climate. And this population are also very vulnerable to climate change that might result in long periods of droughts, and in that case might result in poor or no agricultural production. So this is indeed a very important challenge. What we can do with Earth observation is actually collect more complete spatial information about the distribution of agricultural resources. So one of the fundamental pieces of information to monitor, to map and monitor agricultural resources is to extract agricultural field parcels. So that means that's the basic information level to build a database of agricultural resources. And it's also enabling various digital agricultural services. So by having a GIS layer with polygons of agricultural fields, we can then attach additional attributes of information regarding the type of crops, the owners, maybe the farming practices, the expected yield, and so on. However, in many low and middle income countries, there is not such information. So Earth observation can help us in actually mapping and extracting the agricultural field parcels. From the image analysis point of view, this is quite a challenging problem because the images are characterized by complex textural patterns. And if we want to delineate the field boundaries, we need to be able to capture these textural patterns and the transition between different textural patterns that typically are delineating the boundaries of different agricultural fields. So to try to address this problem and delineate the agricultural field boundaries, a few years ago we started this research to design deep learning strategies able to extract the agricultural field boundaries. And in fact, convolutional neural networks are particularly well suited for this kind of challenge, for this kind of image analysis problem, because they can very well capture the texture in the image, and if trained with high quality data, they can well extract the boundaries. So yes, as I said, a few years ago, we started working with convolutional neural networks, as you can see here, in particular with one architecture called SegNet, designed for semantic segmentation. So we use this kind of network to perform a binary classification. So every pixel in an image is simply classified as either boundary or no boundary. So this was the first result that we obtained, and was on one side promising because this tends to give much better results than traditional edge detection techniques. However, the results that came out of this approach had also some shortcomings. I'm not sure if you can see from the figure here in the slide. How can I use a pointer? Like this, I guess.
Yes, laser pointer.
Yes, so you can see maybe that some of this boundary are fragmented. So actually there are gaps on this boundary. So that's one of the problem of this first result. We were not able to extract close contours for the parsers. So that's why we needed to do some additional work. We ended up using a technique called oriented watershed transform, which actually takes the soft output of the neural network and converts this into a hierarchical segmentation. So what you see here is actually a hierarchical segmentation of the agricultural boundaries, and the color actually tells something about the strength of these boundaries. And that was not yet the final product because this was indeed a hierarchical segmentation. We wanted to end up with one segmentation, and we use one additional layer, one additional step, which is called single scale combinatorial grouping, that takes this hierarchy and converts this by optimizing the scale into a final segmentation. So that's the final product of this technique. So if you want to know more, I put the reference here at the bottom of the page. You can see all the technical details of this approach. So we applied this technique to two data sets. In the paper, you find both of them here. I will only talk about one of them, which is in Nigeria, in an area called Kofa. And it's particularly challenging because the agricultural fields are very small, and the boundaries are also very irregular in terms of shape and geometry. That makes the mapping process more complex. In addition to that, most of the fields are not cultivated with one single crop, but with multiple crops. So that makes the problem even more challenging. But we run our model, and these are some qualitative results that we obtained on three different test tiles. And here you see the results of the three steps that I described before. So first is the semantic segmentation, then there is the hierarchical map, hierarchical segmentation, and on the bottom you see the final segmentation that came out. So the results were, well, not perfect as always, so to say, but in general they were quite promising because they could indeed delineate the boundaries, derive close contours that can represent agricultural field parcels. And one of the problem, however, is that that approach was based on the use of very high resolution images, which are, they provide very detailed images, which is very good, but they are typically commercial data that are expensive to acquire. So a follow-up study aimed to actually use Sentinel data, Sentinel-2, which are open and free, and that gives us the possibility to apply this approach at large scale, so at even country or continental scale. However, the resolution is much coarser, it's only 10 meters. So what we explored was a super resolution approach to detect the boundaries at a finer resolution than the 10 meter of the image itself. So we designed this architecture that, well, now I'm describing only at a high level, but basically has several convolutional layers interleaved by nonlinearities, batch normalization, but has also an upsample layer that basically upsample the resolution at a higher resolution, so to say. So we can derive images or maps at 5 meter resolution or 2.5 meter resolution. So which is a very good result. So we apply this in a data set in the Netherlands where fields are larger, but we plan to use this data also for other countries. And one of the challenges when we want to actually apply this method to other countries beyond the Netherlands. In the Netherlands, we have openly available data for field boundaries, so we can very easily create a large training set, but that's not true for many low and middle income countries. So if you want to apply this, for instance, in African countries or in Southeast Asian countries, you need to have a proper training set to train this kind of model. And we were, struggling to find good data for this purpose. So a couple of years ago, we actually received a small grant to delineate, to create a data set of field boundaries in Cambodia and Vietnam. So we used this project to hire an external company that manually digitized a lot of agricultural field boundaries, 500,000 field polygons. They created this large data set distributed across 62 different tiles of 5 by 5 kilometers, distributed over the two countries of Cambodia and Vietnam. So we have released this data set now openly, so everybody can use this data for training, for testing deep learning models. So we also designed a baseline model to extract, in this case, agricultural field polygons. Indeed, our final aim is not just to extract these boundaries in a raster format, but as polygons, because that's the typical format that you would like to use in a GIS software. So here you see like the workflow that we designed that includes several steps that we have seen from the papers I mentioned before. So a fully convolutional network that derives a binary map. Then there is a set of techniques to close the contours, like what I mentioned before with this watershed transform. Here we use a slightly more complex model involving a few additional steps. And finally, we have a polygonization step that converts the raster map into vector maps. And then we can use different evaluation techniques to assess the accuracy of the produced results. Let me just try to conclude mentioning a few challenges, still open challenges. So the coarse resolution, as I mentioned before, is one of them. So one of the idea for further studies is to explore super resolution technique that can further improve the spatial resolution of Sentinel data. And also we are looking at strategy to streamline the full processing chain, because the one I showed before, it's a workflow with multiple steps, but we could design an end-to-end deep learning strategy that optimize the whole workflow. So those are, let's say, future developments that we are currently exploring. Yes, so this, I think, conclude the first topic for today. Let me look at the time. So yeah, still have time. And the second topic I would like to discuss today is related to urban application, and in particular to studies on urban deprivation. So because of the rapid urbanization that is taking place in many countries all over the world, this often results in deprived urban areas, also called slums or informal settlements. And unfortunately, many of these areas are not well mapped, are invisible in many official maps and statistics. So that makes it difficult to have a clear picture of this reality. And in fact, according to UN Habitat, there are currently more than 1.1 billion people currently living in deprived urban areas. So it's as a very important societal challenge. This societal challenge is actually is actually recognized by the UN SDG agenda, and in particular, Target 11.1 aims at ensuring access for all to adequate, safe, and affordable housing and basic services, and upgrade slums. And in particular, the indicator 1111 requires nation to provide data, statistics on the proportion of the urban population living in slums, informal settlements, or inadequate housing. So traditional techniques to provide data to assess this indicator are based on household survey, which are costly, and they are expensive, they take a lot of time, and in many countries, census data is done only every 10 years, and in some cases, even less frequently because of the high cost involved. So what we are investigating are strategies based on Earth observation and machine learning to derive information in support of this indicator. This strategy is scalable, can be applied at country scale, continental scale, is more affordable, and allows also higher temporal resolution. We could create multi-temporal maps, for instance, at an annual basis. So this is one of the research line that myself, in collaboration with several collaborators here in ITC and also outside ITC, working on deep learning strategies, AI-based strategies to map informal settlements. So here you see on the right side an image from very high resolution satellite, and I hope you can try to detect, to identify where is the slum, where are the informal settlements. And now I think you can see it more clearly. So from an image analysis viewpoint, to be able to map this area, you need again to be able to capture sophisticated texture features. So that's why in the past, different texture analysis techniques were used for this purpose. Nowadays, deep learning, convolutional neural networks, and even more advanced techniques such as transformers can be used to address this task. A few years ago, we have, investigated and introduced the use of convolutional networks for mapping in informal settlements. And we use a strategy called dilated convolutions to enlarge the receptive field while not increasing the number of the learning parameters, so keeping the model complexity as low as possible and to avoid overfitting. So nowadays there are more advanced techniques for mapping informal settlements based on more recent convolutional networks. But I don't want to go too much into technical details. Here you see some results that we obtained a few years ago in the context of the study, where we compared fully convolutional networks with traditional CNN and support vector machine. And on the bottom of the slide, you see some qualitative results of the mapping exercise. What I want to mention is that currently we are working in the context of an European Space Agency funded project. It's called IDEA Atlas. And this project aims to use Earth observation and AI in support of the SDG indicator 1111. So the project we use AI-based method, but also at the core of our strategy is the engagement with local community and stakeholders to allow us to better understand the challenges of the slum dwellers, but also to co-design the AI model and collect data for training our machine learning models with the support of the local stakeholders and communities. So we are working with 8 different cities spread over the world. And you can see here the 8 cities that we've been working on. For each of these cities, we have contacts with what we call local anchors, local actors that help us in organizing workshops. We call them living labs. And through these workshops, we engage the local communities and we collect very important training data, reference data for training, testing, and validating our models. So at the core of our strategy is what we call user and data-centric AI approach. So where users and data quality are at the center, at the core of our approach. And the idea of our approach is to use openly available data, mostly Sentinel-1 and Sentinel-2 data, and we want to finally derive a slum extent, so basically map of the slum extent, and to produce a map every year, starting from 2019 to 2023. But in addition to this, so to say, binary maps, also we wanted to produce a slum severity index. So it's a continuous index that actually capture the severity of the deprivation. And finally, by combining these maps with population density data, we can derive the SDG indicator 1111. So that is the city scale metric on the proportion of the urban population living in deprived urban areas. So this is just a little bit on the technical side, the type of convolutional network that we designed. It's a multi-branch network that integrates different data sources. Here you see Sentinel-2 data and also built-up density. So we derive this layer from building footprints, global projects of building footprints, and from there we derive the build-up density, which is a very important indicator, a very important feature for mapping informal settlements. We also prepared the data set, splitting the data into a regular grid and then sub-splitting it in training, validation, and test. We have done this for all 8 cities in our project, and we use this as our basis for the experimental analysis. We run initially a lot of tests using different models, different techniques, and different input data on the city of Nairobi, as this is the city that has well-established reference data, high-quality reference data that we use for training and testing. So we use different models with different model complexity in terms of a number of parameters and a number of layers, and we use this to finally select the network that we use for the rest of the experiments. And here we selected a unit-like type of network with 3 layers. We also explore different architecture, and we explore different data as input, combining Sentinel-1 and 2 and doing different combinations of input data. And finally, the best results were achieved by fusing Sentinel-2 data with pre-computed built-up density. So you see here the results in terms of precision, recall, and F1 score. So if you use the F1 score as an overall accuracy metric, so we derived the best model from it. And finally, this is the results on all the 8 cities. So what you can observe here, of course, there are a lot of numbers on this table, but let's focus, for instance, of the F1 score on so the last column in this table. And the first thing that you know is that these numbers vary significantly from city to city. So what we observe is indeed in certain cities the accuracies are relatively high, but in other cities the performances are really, really low. And we first of all think it's important that we acknowledge that, because most of the papers in the literature tend to overlook the cities where performances are low and just report the good results. And I think it's important to report also the results where the results are not good. and to also reason and discuss why we obtain these poor results. And in fact, we have several challenges that I will comment the next slide. Here are just some of the visuals, so the maps that we obtained for all the different cities. Here are 4 of them. And in general, we can capture pretty well the spatial pattern, but of course, when you look at the details, you realize the complexity of the problem, which is reflected also by the numerical results that I have shown before. One thing that is also very important in this project is how do we interact with our user communities. So to facilitate that interaction, we built what we call a user portal. Is an online-based platform that allows user to log in and to give us feedback on the reference data. So our expert user can log in and provide additional polygons of where are the informal settlements and where are the formal settlements. So in this way, basically, we can show both the predictions and allow our user communities to give feedback. And in many cases, we have actually realized that the map was more accurate than the reference data that was available at that time. We know reference data quality is an issue, and we wanted to use this portal to iteratively refine the quality and the accuracy of the reference data. So after actually refining the reference data, we obtained slightly improved results for most of the cities. So in version 2 of the reference data, so then you see the accuracy obtained after refining and correcting the reference data, so the labels of informal settlements. Okay. As I mentioned before, we have many challenges. It's a complex problem to map deprived urban areas. And here we try to mention the main challenges. First of all, local definitions of deprived urban areas might deviate from global definitions of informal settlements. So there are global definitions provided by UN Habitat, but these are not always the definitions used at local level by municipalities and NGOs and organizations working on this. So we have to take that into account. So we actually use our living labs to collect information about how locally deprived urban areas are defined and mapped. Another challenge, the resolution of the data, of course, of Sentinel data is only 10 meters. So that doesn't allow us to capture information of individual building level, but we capture more information at the neighborhood level. And the other challenge is what I mentioned before, is the reference data quality. So the data set that we used as an initial training set for our model, we know was not always at the highest quality. We acknowledge that, and that's why we wanted to use our strategy, a data-centric approach, where we train our model with the available data, and then we verify whether our predictions, if predictions and reference data do not agree, then we check on the ground, we ask our local communities to double check these areas and see whether the reference data is correct, or the prediction is actually correct and the reference data needs to be updated. In addition to that, we have also another, maybe even bigger challenge, is that sometimes there are no visible characteristics that can be used to distinguish informal settlement from formal settlements. So for instance, if you look at the picture here at the bottom on the left side, in the yellow polygon, you see what is locally considered an informal settlement, an urban village to be more precise. But visually, you cannot tell the difference from the neighboring areas. So even with very high resolution images, you would not be able to really capture such a difference. So this is to sort of wrap up and summarize the main challenges that we face and we are currently working on to address. So these are just some pictures of the living labs and our our workshops with the communities, local communities in different cities of the project. If you want to know more about the Idea Atlas, please check our webpage and you find more information about the project. Looking at the time, I think I'm more or less on track. Let me try to wrap up and draw some conclusion. So in general, I think Earth observation and deep learning, so the combination of these two technologies provide us very useful tool to extract information that can support the monitoring and to track progress of the Sustainable Development Goals. As I said, this tool can be used for monitoring several SDG indicators. In this presentation, I focused more specifically on two application areas, more related to agricultural field mapping, in particular in smallholder farmers, and in mapping urban areas, and in particular deprived urban areas. So, yeah, EO and deep learning can provide very important information. What is also an advantage is not only that it's more efficient than traditional household surveys, but allow us to produce maps, to produce results that are consistent across different countries, across different continents, and also consistent temporally, because we can use, in principle, the same strategy, the same mapping approach for different countries and repeat this over time. Nevertheless, there are many open challenges. The first one, how do we actually transform the results of research activities into operational solutions? That's not always a simple task. So, in fact, the organizations that are tasked to produce these statistics, typically the national statistical offices of the different countries, use traditional techniques, so don't always adopt Earth observation and advanced machine learning techniques. So there is still a way to go to collaborate together with these statistical offices to make sure that these technologies will be used in practice. Another challenge to mention is, are AI model trustworthy? So for decision making. So we need to work hard to make sure that the results of AI model are transparent for the user. So the way we obtain these results should be as transparent, as explainable as possible. That's not always easy. And one of the things that is, I think, very crucial here, and maybe even more important than explainability on its own, is the quantification of the uncertainty in our results. So we need to be transparent. We need to be open on the fact that when we analyze data, for instance, on urban deprivation, there are large uncertainties in the data. We need to acknowledge that. We need to transparently report in our scientific documents, but also in policy-related documents. And finally, if we want to produce results at a large scale, possibly at the global scale, we need to make sure that our model are able to generalize well in different situations, in different conditions. So generalization ability of our model is very, very important. So yeah, I think with this, I conclude my presentation and stop here, and I'm very happy to answer your questions. And thank you very much for listening.
Okay. Thank you very much, Claudio. First of all, thanks for the brilliant presentation. So we have some questions here in the chat that I will ask for you. Just one disclaimer here. Because of the privacy agreements that we shared with all the attendees of the webinar, I will not read the names of the people who asked the questions, just because in the agreement we told that no names will be present in the recording. So because of the recording, I cannot read the names. Okay. So first question is, did you use any pre-trained models for tasks like super resolution or field boundary detection? Or did you need to label the data and fine-tuning the models yourself?
Very good point. So in the study I presented here for the super resolution mapping, we did not use pre-training, but I think it's indeed a good idea. So if you look, this was a study done 5 years ago. But I would definitely consider this. So we are currently actually exploring more advanced strategies for this. And while one way would be also to look at indeed pre-training strategies, foundation models designed for super resolution of Sentinel data. So there is work done already on this. But I think it's a viable strategy to explore foundation model and fine-tune them for applications like field boundary delineation, right? So they can be fine-tuned with additional labels of the field boundaries. Now that we have collected, for instance, reference data from different countries, so that can be done. One also maybe clarification here, we were not directly doing super resolution. We were not super resolving the images themselves, but super resolving the output map, which is in principle a simpler task than super resolving the images. So but we don't necessarily need the super resolved Sentinel image. We just wanted super resolved agricultural field boundaries.
That's great. Thank you very much.
Hope this clarifies.
For the person who asked the question, if you have any complement for this question, please post on the chat. Meanwhile, I'll go for the next one. In cases where high-resolution imagery still fails to distinguish informal settlements due to visual similarity, how do you foresee integrating socioeconomic or ancillary geospatial data like cadastral maps or nighttime light or mobile data to strengthening the classification models?
Yeah, that's also a good point. So indeed, so there are cases where just Earth observation data alone cannot solve the ambiguities, right? In mapping the informal settlements. So indeed, if we want to have more accurate results, we need to include socio-economic data in any form. So if possible, one could actually integrate additional geospatial layers as input to the model, use this for training and for testing. And the real challenge is to get this data, because these are data that are difficult to acquire, and they are not usually available at large scale. They are, very, very difficult to obtain. Indeed, maybe other data sources. You also mentioned nightlight images. This is something we are currently looking into. So indeed, it's another perspective. So you look not only at daylight, but also nightlight images. This can provide an additional information layer to improve results. Tenure security, indeed. If a settlement, we don't see legal rights, we don't see tenure rights in images, but if we have access to cadastral information, then we could integrate that in our workflow. There's also maybe a little disclaimer that in doing that, one also needs to preserve privacy. Ryan was talking about privacy more related to this meeting, but when you talk about mapping informal settlements, and so this is a sensitive map that you aim to produce. So you need to also ensure that you guarantee privacy of the people involved.
Great, thanks, Claudio. So another one. You use it, actually, I'll go for one that I saw that's a complement of this last one, and then I go to the one I was going to ask now. You mentioned validation through living labs. How do you balance between user input and algorithmic prediction when there is a conflict? Do you use it as a ground truth correction or retrain the model entirely?
Mm-hmm. Yeah, maybe I can clarify that. So the strategy is, so the real challenge, the real problem that for several of the cities, the initial reference data that we use for training and testing is noisy. It's not fully updated. It's maybe not comprehensive. It's not complete. It doesn't map all the areas within the cities. So there are a number of challenges. And in our project with 8 different cities, each city has its own challenges, so to say, and data are collected in different ways and so on. So acknowledging the fact that the training data itself is, and also the test data, so the reference data in general is not 100% accurate. So what we know, we train a model with some noisy data, we produce our predictions. But then we use our predictions to produce a map for the entire city, and then we can overlay predictions with reference data, especially on the test areas. But then, since we don't fully trust our reference data, when we see that there is a conflict, as you're saying, so the ground truth or the reference says one thing, but our prediction something else, then we need to decide who is correct. Is our model which is correct, or is the reference data? So in those cases, we typically ask our local communities to validate those settlements, to check, are they really maybe slums, as maybe our model tells, or not? So then that's one way to basically collect feedback. So what we do, actually, we ask our local communities to provide additional polygons, additional reference data, and possibly correct the labels of the reference data used in the first training of the model. So we actually update the data, and ideally through an active learning loop or human in the loop approach, you could use this additional or corrected data for retraining and retesting. And we could actually repeat this process several times in an iterative way to continuously improve reference data and model accuracy.
Perfect. Thanks, Claudio. Another question here, I think this one arrived in the context of the slum mapping as well, but I'm not so sure. So the person asked, you used CNNs, but I think this is valid also for the other applications because many of the applications are based on CNNs. He said you used CNNs. Did you also explore transformers? And what led you to choose CNNs for these tasks?
Mm-hmm. Look, it very much depends on the specific problem, specific. So it depends on the task itself, but also the data. So, for instance, for this work on mapping informal settlements, we explored. Here you see this MB CNN, so the multi-branch CNN. let me see if I can use a laser pointer. Yeah. So this MBCNN. And we also compare with this other model, GLAV2, which was developed in the context of another application for glacier mapping, but it's similar in terms of input data. So again, using Sentinel data as input. This model is actually using, or actually is a hybrid model combining CNN and transformers. So we actually have explored that. We just didn't see in this particular application a large improvement. Actually, it did improve results in this case. Keep in mind that here the model has relatively low resolution, and in this case, that's why we talk about data-centric AI more than model-centric AI. So what we see that what mostly affect the results is the quality of the training data. While the model itself, of course, has an effect on the results, but it's not the main challenge here. So the main challenge in this, specifically now for informal settlement mapping, is the reference data quality. But we indeed explore transformers, and maybe in other, and also in many other applications, we are using transformers for other applications.
Perfect. Thank you very much, Claudio. Another question here, that is, to what extent can a data set, can a model train it and develop it with a data set, a training data set of one country? How can it be effectively translated and used in another country? Are there limitations that may impact the model's performance across countries, or how do you see that?
Yeah, that's definitely a challenge when you train a model typically based on data from one city. The model can generalize within the city, but the transferability to another city or to another country is usually difficult. And it very much also depends on the mapping exercise. So what are you mapping? So if you talk about land cover, land use classes, that's one type of challenge when you want to transfer the model, because, well, you still might have variations in the classes, but you have different kind of acquisition conditions, different, maybe also if you use different sensor with different characteristics and so on. In this project, what makes it particularly difficult to transfer the model is that the urban structure can change significantly from one continent to another. So African cities typically have a morphological characteristics that are very different, for instance, from Latin American cities or from Asian cities. So the transferability is very difficult because of that. And one thing maybe to clarify is transferability is not only depends on the model itself, but it depends on the task that it has to solve, and the differences of indeed urban areas in this case, or the objects you want to characterize in these different domains. So it is indeed a challenge. We are exploring this by, let's say, with the concept, with the idea of extracting interpretable and features with high generalization abilities, so physical characteristics, morphological characteristics of the cities that are more transferable from one country, one continent to another. But this is an active field of research.
Perfect. Claudio, thank you very much for all your contribution and all for the brilliant presentation. So we are reaching the end of our time. Then, yeah, first I would like to thank you, Claudio, thank also the whole audience, and I'll share my screen here just to share a bit of more information about ASTRAIOS, our project. feel free to enter our website. We have our LinkedIn page, X, or that was Twitter, and also our YouTube channel. So all these series of webinars will be available in our YouTube channel and also in our web page. So feel free to reach out, feel free to go through and get more information. So thank you, everyone. We come to the end of one more webinar of the project ASTRAIOS. Thank you all. See you in 2 weeks from now.